Hello and welcome to another Algebra 1 video tutorial. In 11.1 we'll be talking about investments and polynomials. Our goal will be to see how situations in which money is periodically invested in a savings account can lead to polynomials and do the requisite calculations. Alright, so first example here. Each birthday from age 12 on, Jessica has received $500 from her grandparents. She saves the money in an account that pays an annual yield of 6%. How much money will she have by the time she's 18? Okay, so what you'd want to do is make a spreadsheet or a chart or a table or something to kind of analyze this. And then we'll make a polynomial as well. Okay, so on her 12th birthday, she got $500, so she has 500. But then on her 13th birthday, the original 500 she had got 6% interest, so you'd multiply it by a factor of 1.06 because it's exponential growth. Okay, and then add another $500 because she's getting that extra $500 for her birthday. So the total she has then is $1,030. Then on her 14th birthday, the $500 from her 12th birthday has now been in the account for 2 years, so she gets 500 times 1.06 to the second. Then the money from her 13th birthday got 1 year of interest, so that's why it's 500 times 1.06 to the first, and then got another $500 on her 14th birthday. So now she's at a total of $1,591.80. So on the 15th birthday, so the original 12th birthday money now has been in there 3 years. The 13th birthday has now been in there 2 years. 14th birthday has been in there 1 year, and now she got her 15th birthday money. Okay, so but this is to go to the 18th birthday. So how would you calculate that? Well, it's kind of a tedious process. So the original 12th birthday money, $500, it's going to get 1.06. Well, you can tack 3 more years onto this, or you can go 6 years from the 12th birthday, so it'd be to the 6th power. Plus the $500 from her 13th birthday, now it's been in there 5 years. Plus 500 times 1.0, let's see, this should be a 6 here, 1.06 to the 5th power. 1.06 to the 4th, plus 500 times 1.06 to the 3rd, plus 500 times 1.06 squared, plus 500 times 1.06, and then on her 18th birthday she got $500 more, and that ends up being a total of about $4,196.91 is what her total will be on her 18th birthday. Okay, now this is something that's set up pretty nicely for an Excel spreadsheet. So if you are comfortable with only calculating it this way, skip ahead to the next example. If you want to see how it's done on an Excel spreadsheet, follow me along in that, doing this problem in Excel. Okay, so I've already set up in an Excel spreadsheet birthday column and a total money column. Okay, so we're going to go to the 18th birthday, so I just went 12, and then you could add 1 to the previous cell and drag the fill handle down to get that. If we wanted more, I'll show you that in a minute. Okay, so she started with $500 on her 12th birthday. Then what we want to do is we want to make a formula, so hit the equals sign. Okay, then I want to take her $500 here and times it, times is the asterisk symbol, times it by the growth factor, which is 6%, so it'll be 1.06. And then after that, I want to add $500 more, so plus 500. Press enter, so that should be on the 13th birthday was 1,030, which we've seen before. Now, the thing that's nice about Excel is you can just drag the fill handle, so once it gets to the black cross there, okay, drag that down to the 18th birthday, and it should be $4,196.92. Excel rounds up, but remember, banks, when they're paying you interest, are going to truncate, so it would actually round down to 91 cents, but Excel is going to go to 91 cents. So what you'd need to do is probably extend the decimal places to see what that would be, or if you're within a penny, it's probably safe enough. If we wanted to go more birthdays, I can drag this down maybe to her 25th birthday, and drag this down, continue that, and she'd have about $10,507.53 on her 25th birthday if we needed to. We only needed 18th birthday, so that would be our answer right there. All right, the next example. Every year after they are married, a couple deposits $2,000 into an account that pays an annual yield of 6.5%. The couple starts by depositing $2,000 when they're married in 2003. How much money would they have saved by their 10th wedding anniversary in 2013? Okay, so what you have to do is set up a polynomial. So it'd be 2,000. The original 2,000 they saved was getting an annual yield of 6.5%. So you're going to times it by a growth factor of 1.065. Well, that original $2,000 they deposited in 2003 has now been in the account 10 years, so it would be to the 10th power. Plus $2,000 times 1.065. So in 2004, that money now has been in there for 9 years, and you would continue doing this for each, because they're doing it every year, depositing $2,000 every anniversary. So 1.065 to the 8th, and so forth, until you get to the last two. So I'll just write those out. Plus 1.0 times 1.065 to the first, plus $2,000, which would be on 2013. So you'd need a 7, a 6, a 5, a 4, 3, 2. We got the 1 and the 0. Okay. So if you did that, you get about $30,743.12. Okay. Now 2,000 times 10 is 20,000. So they put in 20,000 of their own money, but they're getting about $10,743.12 worth of interest. Okay, if you want to see this on Excel, watch this next part. If you are comfortable just doing this all on a calculator without a spreadsheet, skip to the next example. Okay, so once again, I've set up an Excel spreadsheet with anniversary years here and the total money here. Okay, so they put a 2,000 in 2003. So then the money is growing, so equals the 2,000, so the previous cell, B2, times the growth rate, which is 6.5%, so we times it by a growth factor of 1.065, and then add $2,000 on the next anniversary. Press enter, and then drag that fill handle down, and that's how fast the calculations are going to be. And my column's not quite big enough, so I need to get that a little bigger. All right, so $30,743.12. I should decrease the decimal because we don't need that. But it's kind of nice to have that third decimal so that you can see if it rounded up or down, because you would truncate that like the bank would. $30,743.12. All right, Tina decided to start saving for her child's college expenses right after the baby's born. For 10 years, she puts in $1,000. Then she stops making deposits. Her sister, on the other hand, Karen, has a baby at the same time, but decides to wait 8 years before she starts to save. So then she puts in a little more to catch up, $1,300 for each year for 10 years. They will each deposit their savings into a special account, getting 5.5% interest compounded annually. How much would each have after 18 years? So who's going to have more? So putting $1,000 in the first 10 years, is that going to end up getting more because of interest? Or is putting $1,300 in for the last 10 years before they're 18? Is that going to give you more money? Okay. Now this one's going to be a tedious process by hand, which can be done. I'm going to show this one only on Excel, though, how the spreadsheet, so you can see the values a little bit better. Okay, so I've taken the time to set up the years from 1 to 18. Tina's deposit, she's going to put in $1,000 in the first 10 years. Karen's going to put in $1,300 in the last 10 years. Okay, so she's putting in towards the beginning, she's putting in towards the end. Okay, so the end of the year balance is going to be $1,000.55. So the formula, if you can see that, is going to be B2 times 1.055, since they're getting 5.5%. Okay, then the next one, the $1,000 here plus the $1,055 is going to get a growth rate of 1.055. So you drag that down. Now she stops putting in 1,000 here, so it's just going to be the previous cell times 1.055, and then drag the fail handle down. So she's going to have $20,846.41 at the end of 18 years for her baby's, now not a baby now, it would be 18, college savings account. Okay, Karen waited, so maybe she had other expenses she had to take care of before she could start saving. So she waited 8 years. So on the 9th year, she's going to start putting in $1,300. So that would be $1,300 times 1.055. Then the $1,300 from, since this is the end of the year balance, the $1,300 put in at the beginning of the year gets 5.5% interest, plus the previous cell, E10, would get 5.5% interest. Drag that down to the bottom, and she ends up with $17,658.55. So you can see how saving less early was a better option than saving more later, because you've seen exponential growth, so you can see how compound interest would work on your side, and that's a significant difference, a little over $3,000 more. Well, maybe it's a semester or more worth of tuition, which would add up and be worth it. So save early and maybe a little less, then save a lot more later. Okay, and you can see the spreadsheet illustrates that quite well. All right, the last example. Let's say someone named Arnie won a local lottery that pays $25,000 for 4 years. Okay, part A. Arnie decides to invest all the money in an interest-bearing account. So make a table with a growth factor of X for 6 years, because you don't always know what the interest rate is going to be, so you can play around with changing that growth factor. So we're going to end up making what these are called is polynomials. So in the first year, $25,000. Second year, $25,000 times the growth factor of X, because that's the first year's money has now been in that account for 1 year, plus $25,000 for the next year. Okay, so the third year, $25,000 has from the first year sat in there an account for 2 years. The $25,000 from the second year has now been in there for 1 year, so you get a growth factor of X squared, a growth factor of X, plus $25,000 more. So you can see the pattern here. So the $25,000 originally has now been in there 3 years on the fourth year. From the second year, that's now been in there 2 years, so it gets a growth factor of X squared, plus this amount right here on the third year has been in there 1 year, 25,000X, plus 25,000. Now, they only got 4 years worth of payments, so now there's going to be no more adding 25,000. It's going to be 25,000X to the fourth, plus 25,000X to the third, plus 25,000X squared, plus 25,000X. Okay, but we don't add 25,000 because you're not getting another 25,000. So the money, all of it's just sitting in there and getting 1 more year of interest on the next row. So this will be 25,000X to the fifth, plus 25,000X to the fourth, plus 25,000X cubed, plus 25,000X squared. Okay, so you can see that's a tedious process, but that's each one is getting 1 more year worth of interest, and this is called a polynomial in X because we don't know what that growth factor is. It could vary. So let's say part B, how much will he earn if the interest rate is 4%? How much would he earn if the interest rate is 8%? Okay, so all we'd have to do then is put 1.04 in for X, 1.08 in for X. Okay, so that's all you would do once you have a polynomial, and if you leave X in there, all you have to do is insert the number to calculate that. So 1.04 for 4%, 1.08 for 8%, and I'll also show you how you can change the interest rates quite easily, and we'll make another Excel spreadsheet table for this. If you don't want to do that, you can skip to the end. That's the last part. You can check the assignment out. If you want to see it on Excel, I will show you that as well. Okay, so we're going to check out the interest rate at the end for 6 years, or the amount of interest after 6 years, or the amount in the account. Okay, so now since I want to mess around with changing the interest rate from 4% to 8%, let's just put the growth factor in its own cell off to the side. So 4% first, then we'll change this to 1.08 in a minute. Okay, so I entered the original 25,000, so that's going to be an equals that cell times. Now, I'm not going to put the interest rate, I'm going to put the cell where the interest rate is held. So I'm going to hit C1, and then I'm going to add $25,000 more dollars. Okay, but I always want it to use C1 when I drag this down, so I need to put a cell reference around there, and that's the $sign. So I wanted to lock in cell C, or column C, and row 1 there for that cell, press enter. So the second year gets 51,000. Okay, I'm going to drag this down. So the third year, end up with 78,040. Fourth year, $106,161.60. Now, I have to change this because the interest stops, so I can't, or the payment stops, so I can't just drag this down. So I need to take just the previous cell times the growth factor here. Okay, and then drag that down, and should end up with $114,824.39. All right. Now, what about after 8% interest? So all I'd have to do then, instead of changing the whole formula, I would just type 1.08 there, press enter, and notice how the values change on that too. Okay, and then if I want all these to match up, I hit the paint sign, and then I get these to match up. Okay, so 8% interest. Let's say you wanted only like 2% interest, you could compare that as well. You can see the difference then. Instead of having to change every formula, you just change one number. It makes it quite simple, which is what spreadsheets are supposed to do. All right, that wraps this up. It's kind of a lot thrown at you, but investing in money can be complicated. But if you break it apart, each year's worth of interest, it's not that difficult. All right, your assignment, 11-1, page 659, 2 through 26 evens. Thanks for watching, and we'll see you in class.